Okay, so coming back to this heat transfer problem, 1D, we have a K matrix here. What I forgot to mention is, how do you get these forces? So if we scroll back up, we talked about these things here. So we have these fluxes or forces that depend on the boundary conditions and the interpolation functions at the endpoints. So the question is, what does that look like? And it turns out it's actually very simple. So remember, these interpolation functions at the endpoints are going to be 0 or 1. So psi1 is 1, this one is 0 at the other endpoint, so that means f1 is q1. You come down to here, f2, you evaluate these at the endpoints, this one is 1, and this is equal to q2. So that expression is fairly simple. It's one of the really nice things about the Galerkin finite element method and how these interpolation functions are assigned to be 0 or 1 on the endpoints. So this automatically will satisfy your natural boundary condition, q1 or q2. So plugging this back in to the general relation, here's my K matrix, this whole thing. Here are my delta t's, here is my flux. I'm using the superscript to say this is for element 1, right? Now remember, we want to take this idea for a single element and then combine that single element with what happens on the second element. So that means you gotta think about what happens when you bring this node back together into a single node. So remember from high school physics or thermodynamics, the temperature has to be continuous. So if you're at a single point and I come from the left side, I would get a temperature here. When these things get connected to a point and I come from the right side up to this point, the temperature should be continuous. You should get the same solution at a single point. Other issue is flux requirement. So if I have flux coming in from one side and the other side, to conserve energy, the summation of those has to be 0. The only time this would not be 0 is if I was inputting a flux on this bar. So imagine, remember we did one example where we had a wire running into a bar and this was generating heat from an external source. So imagine you could take a bar and you could put a hot iron on it. You would get an external flux that would require this to be non-zero. But if you don't have an external flux on intermediate nodes, this will always be 0 and satisfy energy. Alright, so coming back to our matrix, I've just rewritten this again. Let's figure out how to combine these elements. So first thing is continuity on temperature. So if I define my element 1 and delta T at node 2, that has to be equal to my theta or delta T at node 1 on element 2. Okay, so if I just come back up to here, these two have to be equal when I put this node back together. So that gives one expression for temperature in the center, and then I have my temperature on the end. Similar relation for the flux. I have flux at the ends, here and here. Inside, that flux has to balance, so I get 3 flux terms. So now I have these 2 K matrices. This is for conduction. Here's my convection relation. Here's how we add these together. So these get applied on, this is for node 1, this is for the center node. This element this is for the element 1, so that has nothing to do with these terms at node 3. Okay, and then this term is for element 2. So you notice this is on node 3 and the center node, right? And it's decoupled with node 1. So this is only, you can consider this a local basis. It doesn't reach out across multiple nodes. You apply the same thing on the convection. This is for element 1. This is for element 2. Now we simply just add these together. And now this is your total case solvent in this form. So it turns out, due to our boundary conditions, you can simplify this down and solve. Because remember, we only have to solve for U2 and U3. We already know U1. That was a boundary condition. So that is known. And we know Q2 is a function of U3. So we basically simplify this down. If you carefully work through this, you'll find that this is the form you'll need. You could simply do this in the general form. Ultimately, you'll get it down to here. The key thing out of this I want to emphasize is how we combine these. So how do you combine to get your K-matrix and also make sure you fully understand these continuity conditions at intermediate nodes. This doesn't only apply to heat transfer, also it applies to displacement, and there's other physical constraints on electrostatics, magnetostatics, chemical potential problems that we'll hopefully give examples on later. Ultimately, there's always continuity and conservation laws on fluxes that have to be satisfied at these intermediate points. And that's another nice thing about finite element is it allows you to break these problems up into small elements and then take solutions on each element and combine them into these very large systems.